A very good evening to each and everyone who have joined us. I am Dr. Deepak, Associate Dean, International Affairs, Saveetha School of Engineering. A warm welcome to each and everyone for joining our SSE E-Talk series. This is the 7th E-Talk of the series. First, I would like to thank our director, madam, for this opportunity and also for initiation, guidance, motivation, and all the support for conducting this SSE Talk series. Then I would like to extend my thanks and thanks to our principal sir for all his support. And then I will also like to thank our vice principal sir for his guidance and motivation. Now today we have with us eminent person, Mr. Ashok Kumar, Manager, Exyte Singapore. Let me take the opportunity in introducing Mr. Ashok Kumar to all of you. He graduated as a mechanical engineer and started his career in Chennai as a tool designer to cater services for TVS Group for 2 years. And after that, moved to Singapore 17 years ago as designer for marine servicing industry. In total, he has over 20 years of experience in the field of semiconductor facility, mechanical, electrical, piping, engineering, technology implementation, O&M design, drafting, and construction. He has completed a variety of successful projects for semiconductor industry, data centers, infrastructure, institutional, healthcare, mixed development, residential, and industries. He has a vast experience that includes supervision, training, field surveying, estimating, conceptual layout, 3D modeling, fabrication drawings, materials takeoff, and troubleshooting in the field of construction. He completed his Masters of Engineering in Technology Management from University of South Australia with Singapore Education Institution. Few years later, completed the VDC certification from Stanford University and implemented various technologies like BIM, VDC, and IDD projects. Currently, his scope of work involves training project team with latest technologies, conducting training in BIM platforms, and support team in doing projects with the use of specific softwares for digital fabrication, developing standards and procedures related to technology implementation, and involved in latest technologies like AR, VR, AI, and cloud collaboration platforms. His specific role also includes mentoring young engineers and provide regional support in technology implementation. I'm very happy to welcome Mr. Ashok Kumar, and please proceed, Mr. Ashok Kumar. Over to you.
Yeah, thanks, Mr. Deepak. Thanks for the introduction. Yeah, good evening, each and everyone who participate in this session. Thanks to Deepak and Saveetha Engineering for giving an opportunity to present on high-tech fab on advanced industries. So without any further delay, I will proceed with that slides, which I have prepared with a structured flow. Later, I will go through on one by one. Yes, Mr. Deepak mentioned about this. This is about me. So in total, about 20 years of experience in different industries, from more than 10 to 15 years in the field of technology development and implementation of technology, and developing engineers, developing people, and also mentoring role, and so on. But currently at the moment, I'm working as a digitalization contributor plus BIM VDC and integrated digital delivery manager for Exyte Singapore. Yeah, so I will straight away jump into that topic here. So today I would like to cover topics like introduction to semiconductors, then I will introduction to fab facility and what is a clean room, and so on. And also introduction to utilities in base services. I'm actually dividing this fab facility in two areas. One is base services, another one is called hookup services. Then how this wafer is manufactured, then chip manufacturing, then talk about high-tech fab and its technologies used in that fab. Then finally, we will go with a Q&A session. This is this overall topics we'll cover today for that. So I just want to start with something, go with the history of semiconductors. Before I go into the topic straight away, I just give some history about semiconductors. As you all know that the semiconductor history starts in 1833. The first documented observation of a semiconductor effect was done by Michael Faraday, 1833. He was the one noticed that resistance of silver sulfide decreased with temperature than the dependence observed in metals. So he's the one first observed. If you see that the conductor, there are elements as conductor category and insulator. There is in between. Is called semiconductor. That is the one using the material like silicon, germanium, and carbon. So it will be categorized under semiconductor here. Then just give an introduction here. A semiconductor is like is a solid state substance, as you all know, just that is halfway between a conductor and an insulator. Then a transistor is a basic element used in building semiconductor devices. So just a brief explanation about this semiconductor and transistor here. In 1904, the two-electrode vacuum tube is invented. You see that how big is this two-electrode vacuum tube? Actually, this was John Ambrose Fleming is the one used Edison effect to invent that two-electrode vacuum tube rectifier. So it actually plays a major role later stage in that in the electrical design. Then this is an interesting aspect here. You can see this world's first general purpose computer ENIAC is announced in 1946. There was some interesting history about this. This computer was weighing 30 tons, occupying 160 square meter room, and more than around 18,000 vacuum tubes. So, but these vacuum tubes always has problems. In every 2 or 3 days, it has to be changed. But contrast to that, today, tens of millions of transistors are yet smaller than palm of our hand. You all know that we are carrying mobile phones, we are carrying a lot of electronic devices. So because of this IC's introduction, a lot of evolution happened in that semiconductor field. So if you see this picture here, this is that ENIAC computer here, just for an introduction. Then in 1948, junction type transistor is invented. If you see that, there's the first junction type transistor is invented in 1948. Then 1955, Japan's first transistor radio is released. Okay, I just ran through that history here. So if you see this, the Kilby patent refers to the patent of the basic concept of the integrated circuit. It was first developed by TI, a Texas Instrument, which is in 1959. Okay. I can put more histories on that, but just an introduction about semiconductors starting to now how it is evolved. So Moore's law, I'm actually putting here this Moore's law. This is the who actually later became a co-founder of Intel. Predicted that he actually predicted that integration rate of LSIs. LSIs is the one which I have explained earlier. It double every 18 months, implying, and also it becomes 1,000-fold denser in 15 years. What he was predicted came to reality now, turned to reality, almost exactly what he predicted. So number of transistors on same chip would double approximately every 2 years, which is happening at the moment. Okay. Okay, I'll give an introduction to FAB. Today, our main topic is about high-tech FAB. In microelectronics industry, the semiconductor FAB is called something. FAB means something needs to be fabricated. Here, the FAB, commonly called a FAB, what is fabricated? IC is fabricated there inside integrated circuits or manufactured. So that's why we call it as a semicon FAB. So I put an image here in the next slide. You can see this is something like a typical FAB, looks like that. You can see makeup air unit at that basement level, then clean sub fab, and supply plenum. So this is something like a typical FAB looks like. Okay, so if I put in another overview and explain to you how this FAB looks, see here at this basement level, or we call it as utility level, maybe a different project, they call it as different level names. You can see facility plant equipment will be placed there. Electrical distribution will be at that clean sub fab. Then this is the sub fab level 2. Then tool supporting equipments. The tool supporting equipment is the one will be placed in those tool supporting equipment will not be placed in clean room, but main tools will be placed in clean rooms. I will later cover that, what is clean room and all those informations. Then this is called the hookup services. In the beginning of the presentation, I mentioned about two things. One is called the base services, another one is hookup services. This is the hookup services. Later I will cover that portion in detail. Then this is called laterals. Laterals is the one helps to connect utility services to the main tool. I will go in detail later on. Then the tools, the main tools, which is this is not a one tool. It may be hundreds of tools in that clean room area. It is a one helpful in preparing the IC chips or manufacturing of IC chips. Then clean room and fab, you can see it here. Okay, just give an idea here about the typical fab wafer fab facility, how it looks, what are the things needed for this wafer fab facility. If you see in that picture shown in the typical fab facility, it is catered with continuous supply of services. If you see from the left, there is an arrow, raw wafers and other materials is going in here. On that right side, you can see another arrow, finished wafer is there. There are plenty of operations and or plenty of process need to be happen in that wafer fab facility. And for that processes, it needs to have a lot of gas storages, solvents, chemicals, DI waters. Then also we need to maintain that area of an environment. Also we need to maintain it properly. So that typical fab facility will be looking like this. So you can see on this box here, this is that we call it as a clean room area. So all the facilities will run through here. As I mentioned to you before, the services coming from sub fab level to the main level. Later I will go in detail as a video and also showing some animations on this part. So we will so in that previous slide, you see here there's something called clean room. Clean room here, you see this is the clean room area. So this is that key element central part of the fab is a clean room. So we are going to discuss about that clean room here. So what is that the clean room will do? The central part of a fab is a clean room, an area where the environment is actually controlled to eliminate all dust particles which is less than 25 micron or nanometer in size. It has to be controlled. Dust is equal to 25 micron size, but some of that small speck particles may be lesser than that, 0.5 nanometer in size. So it has to be controlled. So next one, I am going to show you an table here. Just go through that. So this is that classes on the left side, and also what is that ISO equivalent for that. If you see that class 1 to class 10, class 100, and so on, some of our clients has a clean room which is class 1 and class 10. So means that, what does it refer to here? If you see here, one human hair is equal to 100 microns. Dust is equal to 25 microns. Other contaminants is 0.5 microns. I give a small explanation below. Semiconductor memory chips are manufactured in clean room environments because the circuitry is so small, even tiny bits of dust can damage it. You can see that scenario below. In a class 1 clean room, there's no more than one particle of dust in a cubic foot of air. Where is that? This is the thing. The 0.5 nanometer in size is that one dust particle only in that class 1 clean room. So there are some of the clients, they have clean room class 1 and class 10. But if you take the same comparison, a clean modern hospital has about 10,000 dust particles per cubic foot. Now you can actually imagine that how clean is that a clean room. There are different types of clean room types. Clean rooms, if you see on the left side, which is called ballroom layout, which is a continuous clean room. There is no partition or any bay in between. But if you refer to the next one, which is a bay chase layout, this is clean room, there's a bay chase here, clean room, something like that. There are different types of clean rooms in there. Then if we go to this ballroom fab, a clean room ballroom fab, this is one of the type of clean room. You see on the top, this is a pressurized plenum, ballroom fab here, clean sub fab, utility level. So whenever there is a pressurized plenum, will pass the air to the fan filter units, and the air will flow into here, and all the return air will go through the floor and go underneath this rise floor. You see that next one, which is called rise floor. In that rise floor, I will cover that later. What is that rise floor and all these functions I will cover you in a next slide. Then one more item which is called waffle slab. If you see that in that ballroom fab, this called rise floor and waffle slab here. What is that waffle slab means? A waffle slab is a type of slab with actually holes underneath, giving an appearance of waffles. It is usually used in the places where large space are required to avoid many columns. In case if we need more columns need to be in that place, we will use waffle slab to avoid that. To actually avoid many columns interfering with space. It has a good vibration control also. Vibration control capacity and load carrying capacity as well. You see that this is a typical waffle slab here. Then this is the view. As I mentioned to you, this is this rise floor. You can see here rise floor, and this is called pedestal. This is called viewing panel. Sometime if you wanted to view some things, what is going inside certain things, you have to view it. Then there will be a something called viewing panels here. Then another item, if I go back to the previous slide, in that waffle slab, there is a hole, circular hole. Some of the slabs may be square, some of the slabs may be having circular hole. If you see that in the next slide, there is a call pop outs. You see here pop outs, which is just below that rise floor. These pop outs will help to route the services from level below, sub fab, clean sub fab to fab level. All the services will come through this one. I will show you in the next slide. You will understand. You see here, this is the services coming through, and it will be locked, and there is a cover for that. So any services to reach clean room area or clean room tool, it has to go through this pop out. There is no other way or no other external entry into that clean room. So it has to go through this pop out area. Okay, next I will come back to this rise floor. What is that rise floor meaning? There is a space between the rise floor and the concrete slab on grade is used. Why they need this rise floor? Because they have to control the environment with a correct pressure, temperature, humidity, and all that information. What they will do, they will use that return air duct. They will use that space between rise floor and the floor slab. They will use as a return air duct, and also they will use that space for the area of wiring, cable, and piping. They will use that area. And also perforated panels provide a way to achieve flow conditions like airflow, particulate contamination, and vibrations. It will actually helps to they will use that space for that purpose. And also there are different types of panels they will use for this rise floors. Maybe according to the application it will vary. There are some of the materials are aluminum, fabricated steel, aluminum casting, wood core, gypsum, and cement, or some of that rise floor they will use here. See here, the pressurized plenum is here. The air will go through this. The air will go into here through the fan filter unit. Then the air go underneath that thing. They will use this area as return air duct. Then the air will be circulated like this. The air will be circulated. No other way it will go. It will go underneath the floor only. Then if you see this pedestal here, then this is the 3D view of this, how this looks. This is the tiles, or we can call it as a rise floor by partition. Then this is that the view took from the bottom of that. Underneath that rise floor, you can see all the pedestals, and there is floors here arranged. So all the services will be go underneath here. I will show in a next slide. Just give an idea about that. So before that, I would like to tell you in that fab, I divide into 4 things here. In the fab facility, installation of base services until LPOC. Maybe that term may be different for you. LPOC means lateral point of connection. I will explain that. What is that lateral point of connection? Then these are the services will be involved. Archi and structure, which is actually infrastructure, you call it as, or envelope for the facility, archi and structure. So architectural involves facades, doors, windows, and all those things. CSA is columns, beams, and all that stuffs. HVAC is for ventilation and air conditioning systems, exhaust systems, bulk gases and chemicals. And these are the things which needed for tool operations. For the tools, it has to gone through a quite number of process. It has to gone through. So you can see it here. And then the next one, if you refer to here, which is installation of hookup services between LPOC and TPOC. So these are the process, and these are the tools it may have. It has to install there, and I'll run through this tool installation in clean room. It will covers installation of tools, AMHS, which is called automated material handling system. I will go through all the videos in a while. I will run through a bit quicker. Then chip production. So I'm focusing on all of these areas here. Then come back to here, which I mentioned to you in the previous slide. There's something called base services until LPOC. I will give in the next slide what is that LPOC. You can see here, this is called LPOC. In the base services at clean sub fab, which is called level 2, they will stop the services here. From here, the utilities will be connected under the waffle slab through the pop out, reach the rise floor and connect to the tool. So that is called hookup services. I will cover that in a while. You see here, this is that some of that services. I'm just giving an idea. All the services is connected from LPOC, then connect back here, which is above the waffle slab, but inside the rise floor area. You can see here, this is that waffle slab, pop out, the service come up, you can see that information here. So this is called TPOC. So in that slide number, previous slide, I mentioned about LPOC, then this is a TPOC, means it has to connect to the clean room tools. Okay. Then I talk about AMHS. What is this AMHS? Why we need this automated material handling system? You can see here, wafers are moved between different tools and processes. There are quite a number of tools in the clean room, not only one tool, maybe wet etching, dry etching. There are quite a number of processes it has to gone through. So what this AMHS will do, wafers are moved between different tools and processes using the automated material handling systems called AMHS. So each wafer may be moved through 1,000 processes. It may be moved through a different process. Some maybe 800, 900 process, some 1,000 process or more than that. It takes more than 1 month to make a memory chip. So it has to gone through a lot of process. You can see here, this is this material handling system. It will run through this. It will go and reach to the different parts. You can see here, this is that path here, that AMHS, it will run here in this path. Then the next one, I told you this thing is called FOUP, FOUP. Front opening unified pod. It is a specialized plastic enclosure, actually designed to hold silicon wafers, because it needs to carry this in a control environment from different machines for processing of various processes. So it will carry the wafers. What it will do, it will travel around this and go to that specific machine. It will drop down here. They will use this. They do some process. After that, it will go up. It will actually go through a different machines and different processes. And then another thing called central utility building, which is called this building supplies, because any plant, if you want to operate, it needs a mechanical and electrical energy to the entire plant, right? So that mechanical and electrical energy is supplied from the cup building. So the cup is separated from the fab by the specific loop or road, and the typical facilities will be in this chiller plant room, electric rooms, scrubber yard, and so much things. It will be covered in that. So this will be a separate building. You can see here, fab by the service road or service tunnel. It has to be go through this. It's a separate building. Then I will give an idea about here. Now we have gone through about what is fab, what other things need to be inside. That just give an introduction of the fab here. Now I will show you about overview of wafer and chip manufacturing processes. How the uh, wafer is manufactured, what is the material, and so on. I'll give an idea here. So the introduction to wafer manufacturing, the material most frequently used in semiconductors is silicon. So this is that most frequently used materials. For information here, abundance of silicon in earth crust. It's, you can see that a percentage here next to oxygen. The second most abundant element in earth is silicon. So it is most frequently used in semiconductors. Okay, there are some of the ways we can get this silicon is found in a lot of things on earth. I can see here rocks, natural water, plants, trees, bodies of animals, and so on, many items. Silicons used in semiconductors such as integrated circuits requires very ultra high purity, which is equivalent to 11 nines. 99.9999 is very high purity and is refined using various processes after extraction. Later in a moment, I will share you where I will show you some videos. This is some of the silicon manufacturing methods. At the moment in the market, we are having 8-inch wafers. Now also some places they are producing 400 diameter wafers. The methods like ZochRalski method or float zone method, a few methods actually is available to actually produce these wafers from silicon. So while the largest silicon ingots produced today are 400 in diameter, but at the market, most common one is 200 and 300 diameter crystals or standard industrial processes. What is this ZochRalski process? You can see that I just given information here. So any silicon melt, we can put in a we can collect all that silicons here, raw material, and it will be used this seed to pull this here. This process will be repeating again and again. I will show you in the next slide for a better understanding. See here, this is the raw one, melted, seed comes in, go here, then the feed starts. Then this is the final process from A to H. You can see here that full process here. You'll get the final output product here. Okay. For example, this is my this is another representation of that. If you see that this is the raw material, I put it there. Then the next step is melted. Seed here comes in, started, crystal growth started. Then the final ingot will be like this. The final ingot, maybe 300 diameter or 200 diameter, it will be like this. Let me share a video here, the next one. Just have a look on that video. Okay, now you can see that end product here, it's finished. Then I will run through that process here. After once ingot is produced, what are the process it has to gone through here? You will see here um, process like peripheral grinding. Once we have that ingot, we have to grind to the specific diameter here. Ingot is cut into some blocks having the specified length. After its periphery, you have to do the grinding. It has to gone through that slicing process for this. Then we have to gone through the process like beveling, lapping. Lapping is something like wafers are set in carrier, which spins between two two rotating lapping plates. Both surface of the wafers are lapped to remove damaged surface layers and all that. This will be done in um, lapping process, etching process, which is chemical polishing, then followed by heat treatment. In that heat treatment, you will see that there is heat treatment is applied to eliminate thermal donor in order to restore the originally intended specific resistance. There is some process happening during this heat treatment. Just give an overview of what are the processes here. Then polishing, we have to do the polishing here, mounted on a ceramics plate. We mount on a ceramic plate here, pressed against the surface of a rotating plate covered with a polishing cloth. Then we do that polishing here. Then after that, cleaning has to be done. Wafers are physically and chemically cleaned using ultra pure water and chemicals. And also we will do some here inspections. Inspections like wafer flatness and surface cleanness will be checked, or the key factors of substrate. Then packaging, and then shipping. Shipping has to be done placed in a shock absorbent shipping boxes to avoid the shocks. So these are that overall process, the wafer manufacturing process. Ingot is manufactured, then go through the step by step, then finally the wafer is shipped, right? After that, let me show another short video about the process which I shown just now. So finally, we use this polishing here with the help of this tool here. Then once this operation is done, it go for testing, then followed by packaging and shipping. Yeah. Okay. Then so in this slide, if you see here, we have done this wafer slicing front and processing facility. So we will further check about overview of wafer and chip manufacturing process. The wafer has been done. How that wafer will be transferred to a chip. So that will be under this chip manufacturing process here. Let me show you this picture here for an idea. So for now, we have gone through that crystal production here. Crystals from raw materials, create the ingot, wafer production. Then we have to gone through for the chip productions here. Okay, the next slide. What we are going to do is we take this annealed wafers. We have to gone through for process layering, epitaxy, oxidation, and so on. There are some processes it has to go through. See here, if you've gone through this epitaxy, oxidation. Epitaxy is something like a single crystal film of a semiconducting material is applied by a chemical vapor deposition or some other process it has to gone through. So metallization is another one. Then this is called the layering method. Then followed by, if you see that epitaxy here, I just give some information about those process here. What is that epitaxy and oxidation? I think that since the time is running out, I'll just go through on that process here. Metallization, a thin film deposition. So you can see that there's a layer by layer. Next step is called a planarization. Planarization is another step. After each of the layering step is done, a chemical mechanical polishing step smooths the surface of the wafer. So this planarization will helps to, which is called chemical mechanical polishing, CMP, will helps to smooth the surface of the wafer. Then the next one is coating with photoresist. The process, I'm just go through the step by step in developing the chip manufacturing process. Then for the photolithography coating techniques, there are different types of coating techniques here: spin coating, spray coating, dip coating, and roller coating, and so on. This is the first step, coating with photoresist. You can see here. Later, after this end of the slide, I will share some video. Then this is for coating with photoresist. Then the next process is the masking. Masking is a pattern sheet that shields a semiconductor material through wafer exposure. This is one of the process in photolithography. I don't have much time to go through all these things. You see here, this is that schematic diagram, how this is transferred into a 3D layout of components in a chip. So using the masking technology, they will do this. Then using this mask design, it will divide the structure into actually horizontal layers, capture the design of each 2D layer in photo mask. So these are the steps, and these are the processes it will be happen during this step number 2. Yeah. Then exposing technique. This is one of the process. Some of the exposing techniques. Exposing is something like a wafer is exposed to ultraviolet light, which changes the solubility of the photoresist in the unmasked areas. That is the main purpose of this process. Some of the exposing techniques you can see here: contact aligner, proximity aligner, or project aligner techniques. You can use that. Then the next step is called developing process. Developing is something like photoresist coated wafer has been exposed to light. It is immersed in a solution, some solution called developer. So that is a step number 4. It is actually formulated, so that why we do this process, it has to be formulated to be removed. Maybe some of the acidic areas are exposed. It will be dissolved in that developer. So that is the reason we actually go through this process. Then the next one, then I will just give a recap here. What is this? Substrate, apply photoresist, expose to light, apply developer. So these are the some of the steps here. If you go through this etching, stripping, photoresist, and cleaning process. So some of the stripping photoresist methods here are chemical stripping, plasma etching. These are the processes it has to gone through. So each and every chip has to gone through all these processes. You remember that's the reason I mentioned in this automated material handling system, each wafers has gone through more than thousands of processes, and it has gone through different machines. So there are a lot of processes it has to be done. So this is the patterning, layering, patterning. This next one is called doping. You will see that the doping, which is a thermal diffusion or ion and ion implantation. So this thermal diffusion can be done to actually wafers will be placed in this quartz tube. Then the gas will be flow through these wafers. This is for the thermal diffusion process. Then ion implantation. So later I will show one of the video to cover this entire flow here. So this process, it will be repeated again and again to make sure the final product will get, until the final product will get, the process will be repeated. Then there is an passivation will be done after the wafers have completed all the layerings. It has quite number of layerings has to be done. As I mentioned, it has to all the process in this chip production, it needs to be repeated for it has to complete all the layering, patterning, and doping cycles for the chip being made. The chip circuitry is complete. Once the chip circuitry is complete, passivation is a CVD type process that coats the wafer surface with an oxide layer. It will coats on that chip. They will coat oxide layer on top of the wafer surface. Then finally, you will get the on wafer chips ready for testing. So once it is done, it is ready for testing. Now it will go for the wafer test and backend processing. If you see this thing here, so we have gone through these steps here, all these things we have gone through. You can see here, this is the way it is built up. As I mentioned to you, there is a repeated processes, right? You see build up one wafer surface, one small chip wafer surface. How many layers it is built here? You see here, silicon transistor layer, multi-layer wiring layers, then wiring, and so on. This is the wiring layer here, then multi-layer wiring layers. So it reach up to this. Once it's done, then the next process will be dicing, packaging, and so on. Then this will be the end product. In this link, there is one animation. I don't have time to run through that animation. If time, let me see if I can. You can see my screen here, that animation screen. So if you see that, Mr. Deepak, you can see my screen, this animation screen.
Yeah, screen is visible, but
Okay.
I think it's okay if we go skip animation and we can proceed also. No worries.
Okay. Okay.
Yeah.
Okay, then I think the time is running out. We will go through the next one. Okay, the chip production video. This is a short video here. Yeah. Then finally, if you do the probing and so on, the final product will be something like this. Okay, I will skip this. Then I just come back to this high-tech fab. That high-tech fab, um, I divide into. I just run through quickly. So this is that. What is that high-tech fab? Um, Digitized all the workflows in producing this virtual design model of the buildings and facility systems, plus hookup services, plus digitized workflow in chip production process. So I just give an introduction about what is the BIM technology. The BIM is about building information modeling. If you wanted to develop your facility, uh, you need to have this technology so that every stakeholder, they can talk each other. If the model is developed by architects, it can be transferred to the structural engineers or civil engineers or MEP system engineers. Then finally, the model, the information can be transferred to the builders for construction and transferred to the owners for maintenance purpose, so that the entire project life cycle, the information will be evolved. This is just an idea about what is BIM, what are the softwares is used. It will give an idea here. Currently, there is you are using AutoCAD, which is called the 2D environment. If you add that Z-axis or space, if you are dealing with spaces, then it will be a 3D. If you add time to the space, which will be 4D. Then cost, if you include, it will be a 5D. Then sustainability and the energy analysis or anything, it will be a 6D. And operations and asset management, if you're dealing with, it will be a 7D, and so on. So why BIM is important? The reason, the contract deliverables is changed by the government and the government bodies, and some of the areas it will be mandatory. That's the reason the deliverables is changed. Another reason is the projects are so complex. You see that in the picture, these are the complex buildings. If you wanted to build, we can't do that just do by normal traditional drafting. So we need to have some softwares, technology based softwares we have to use to do this. So to get this kind of increased to actually cater this increased project complexity and achieve the timeline. Then the building information modeling, it helps to reduce errors. And also the main thing is collaboration. The collaboration across all the stakeholders can be done seamlessly. Then how this BIM works, I just run through. There is a few items quite useful for you. The traditional way, this is that traditional by manual or whatever, this is the workflow. When it comes to BIM, this is a model centric workflow. From that 3D model or digital model, we call it as, all the informations can be extracted. There's a BIM called interoperability, has that function. For example, I'm using software A, then another party using software B, then these two software has to be talk each other. If they don't talk each other, then there will not be any information sharing. Then that is a concept called interoperability comes into picture and solve this. Then the clash detection. If you want, if you are doing a construction related things, you need to install a clash free one. For example, for our fab, if I want to install the services, it should not clash with the other services. It should be detected in advance. So BIM is having a technology to detect all these things, the identify costly clashes, it will identify, and also it will helps to reduce this RFI, which is called request for informations. It is helped on that coordination area. So if I use this BIM, I have a clear coordination and my installation will be perfect. Then on top of that, a coordination, once the coordination done, you can see here is a clash free model can be developed using that BIM technology. Then the virtual reality, as I mentioned to you, uh, the virtual reality is most widely known of these technologies. It is fully immersive. You can feel in another world. Apart from the real world, you can feel in another world using a head mounted display. You can put a HMD on your head and you can feel that. You can do a design reviews. For example, if you are doing models, you can do a design review with the multiple parties just with that head mounted display, you or call it as a headset. you can actually experience a real computer generated world. It will bring into you that like you're using apps like Pokemon or others in the mobile apps, or an example for that as well. Then now it's another one called mixed reality. So mixed reality, what it will do, it will brings together real world and digital elements together. That is that mixed reality. You can see here, this is that real world objects inside, and you can we have done that function recently, implemented this. You can just stand in a room and you can see that objects. So it will link up real world and digital objects using that mixed reality. Then scan to beam is another function. If I use this a scanner to scan that particular facility, it will tells me what is installed or what is built. I can compare this with my model. Digital model may be different, maybe contractor, whether they follow this or not. This can be easily tracked using scan to beam. You can see here, this is you can see here, this is that scan to beam here. This is the scanning here. This is the actual one. You can do a comparison. Then offset fabrication. Offset fabrication is a process which involves the design and manufacture of complex items outside the site. So we don't need it will improve space utilization, lower the cost, and all that. It will be very helpful in that area. You can see here, there's a BIM model, there's a fabrication shop, and it is installed here. This is called offsite fabrication. Then the fourth dimension, which I mentioned to you, this is my 2D drawing. Starts with 2D, 3D, then add a timeline on top of this. And also using the fourth dimension, I can do a status tracking here. So this items is installed, how many percentage is covered. This kind of informations can be covered in the fourth dimension. And also fourth dimension, you can have a construction sequencing. I just quickly run through. You can see this is my design model. I can track here using my project management software like a Primavera or a Microsoft project. I can check here. The end of the day, it will run through the schedule. For example, week number 1, what happened, you can see here. Week number 4, week number 5, it will be finished in actually how many weeks. So you will see the final object here. This is called digitally rehearsed before it is actually built, something like that. Then this is the construction sequencing for 4D. Then talk about a fifth dimension is the quantities plus cost. From this model, the quantities can be taken and how much cost, so we can have the overall cost for the project. Then we can track the cost by services or by the discipline and so on. We can have more features to track this using that fifth dimension, which is the one of the technology of the BIM. Then as I mentioned to you, BIM can be used for analysis also. As you are engineers, you may have to do architectural analysis, structural analysis, lighting analysis, mechanical analysis, like linked with softwares like train trace, E20 softwares, Dialux. So what BIM will do, it will export these informations to that software. Then from your main software to the analysis software, easily you can do the analysis and get the results. So it is very helpful in doing the analysis as well. Just show some examples here like internal CFD, shading analysis, dynamic thermal modeling. So there are some softwares called IES. It's actually available. You can use one of the softwares to do the analysis. Then on top of that, let me show one simulation here. You can see this is called a sun shadow study. Using that BIM technology, you can do a sun shadow study. You know where the sun path is, so you can decide where you can place your glazings to avoid the additional heats entering into that building. So this kind of things you can do. And on top of that, there is another analysis you can do here. So wind analysis, how the wind flow. So there are different types of analysis as per your requirement you can able to do. Then I would like to summarize here overall. Actually, yeah, managed to finish in time. I just given a summary here what we have covered. So we have covered introduction to semiconductors. So introduction to fab facility and clean room, how the fab is constructed, and the clean room concepts we have gone through. An introduction to utilities, what are the utilities and services, and base services and hookup services is covered. Then we talk about wafer manufacturing, from ingot to how to reach the wafer manufacturing. Then chip manufacturing, from that wafer, how it is converted by different process it has gone through and create these chips. Then we have gone through about high-tech fab and also various technologies used in high-tech fabs. I think this concludes my presentation here. I'm open to Q&A session.
Yeah. Thank you. Thank you very much, Mr. Ashok Kumar. It was
Yeah.
really a wonderful presentation. We have covered various aspects, starting from a basic fab to an high-tech fab, and also various process in chip manufacturing. And also you covered a lot about BIM technology. I'm sure our faculties and students who are watching through Zoom and also through Facebook Live will be benefited out of your presentation. And thank you very much for your very slow and steady presentation. It was very clear and I'm sure it would have been very helpful to all of us. Now let's open the session for question and answer session. Like participants, you can ask your questions one by one by introducing yourself. So please unmute and then you can ask your question.
Good evening, sir. Myself, Dr. Kalyan Sundar from Department of ECE. Is there any scope for rubber preparation in India as of now? And if it is so, what is the packing density available in India?
Yeah, at the moment, yeah, I can say that there is some plans from my clients. What I heard is there's the plans for them to put up a fab in India. If I'm not wrong, somewhere in Bangalore. I don't have the firm details about that. The diameter will be about they're planning for 400 diameter wafers.
Okay.
Thank you, sir. Thank you.
Okay.
Thank you very much. Then any other questions? From the participants, from civil department, from mechanical department, faculty, students, if you have any queries, you can please ask. So BIM technology is very close to civil. Anybody else? Okay. So if there are no further questions, like already the speaker has shared the mail ID, I will also share the same with all of you. You can always write in person and then clarify your doubts. So thank you very much, Mr. Ashok Kumar. It was really wonderful to host you and then to listen to your presentation. And you have even spent almost 2 to 3 weeks with me in arranging all these things and to understand the process. So you have spent a lot of your valuable time. We really value that and thank you very much for that. And I'll also like to thank once again our director, madam, principal sir, and vice principal sir for all their support and guidance. And also I thank all the participants who have joined today for the session. Thank you, everyone. Thank you very much, sir. Have a good day.
Yeah, thank you.
Take care then.